Mr. Harridan here. This is electron configurations and orbital diagrams. Another great fun topic here. Okay, that was kind of weird. Well, you know what this...
Legend. Wait for it. Dairy.
Okay, that's a little better. Now, electron configurations and orbital diagrams. First, we're going to talk about orbital diagrams. And nobody can see that pen cover, Mr. Harridan. Okay, orbital diagrams. And then you pick this one. Okay. These are the ones with the boxes. Okay. And they have the arrows, and it shows all the information about all four quantum numbers that you need. Okay. Then there is something called an electron configuration, which doesn't give us as much information, but is a shorter way to show the arrangements of electrons. Okay? Okay, so we need to do some background information before I show you how to do this, right? Remember, n is the distance. Energy and distance. Remember, n is a number from 1 to 7. Okay? The relationship between n and distance must stay true. Electrons in the higher n are more likely to be found further from the nucleus. Okay. Here's the problem. You would think that we would have a perfect order to mix this, but unfortunately, we get all mixed up. Okay? So this is not the order we're going to use. There is a order according to the periodic table that you have to fill these. Okay? For now, trust me, I know what I'm doing. Thanks. We're going to ultimately show you the periodic table provides you the perfect arrangement for the correct filling order. Okay. Remember that the valence electrons are the electrons in the highest level n. The highest energy electrons are in the last sublevel that you are filling. Okay. Now we need to go over three great rules. We have to go over the off-ball principle. Okay? Took me a while to figure out that this off-ball principle, there's nobody named off-ball. This is a German word for lowest. It's German. So electrons are put in the lowest amount of energy first. Meaning, start with 1s2 when I do this. Okay? And then when you're going to end, that's going to be the highest energy. Then we have the Pauli exclusion principle. The orbital can hold 2 electrons. Two! Just 2. It's an exclusive club. It can only hold 2 members. See? Here's an orbital box. You can only put 2 members in it. Clockwise spinning electron and a counterclockwise spinning electron. Okay? This is important as well. No electron can have the same 4 quantum numbers, because each electron has to have its own seat. You know, so we can't have 2 people sitting in one seat. Okay? And they have to have opposite spins. That's why we have clockwise and counterclockwise there, right? And then we got Hund's rule. He does rule. He's a great guy. I love Hund's rule. When filling up a sublevel with equal energy, 1 electron each holds. Each orbital holds 1. Is that what it's supposed to say, Mr. Harridan? Sure, Mr. Harridan. Holds 1. Then they double up. It's like, okay, Mr. Harridan, what do you mean by that? Okay. Suppose we're doing a 2p4, right? Okay. 2p4. First, we're going to do it the Rongo way. This is a p orbital, right? There are three p-shaped orbitals. So you're going to see me draw three boxes because there are three p-shaped orbitals. Okay? This right here is the number of electrons, the 4, when I do that. Okay? And then this is the principal quantum number. Okay? So I'm going to be putting 4 electrons into this box, and we're going to be doing it wrong. Here's how you do it wrong. You go doop, 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 doop. Nope. Wrong O. You can't go up, down, up, down. No. You have to do your bings before you do your bangs. You have to put 1 in each one of these. This is going to be righto. Okay? So you have to put 1 in each one of these 2 P's. So you put uno, up, 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 and then you do down. You have to do your bings before you do your bangs. That's what I say. So you go bing, 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 bang. That's how I do it. Okay? You gotta go up, 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 down. That's what Hans rule says. You can't go up, down, up, down. No. Up, 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 then down. Okay. You'll see me do plenty of examples and explain that to you. You know how that is. Okay. Time to do this great table about ions. Because everybody loves a great ion. Most metals will lose electrons and become isoelectronic with the nearest noble gas. When they lose electrons, they will be smaller than the original atom because you're losing electrons. Nonmetals will gain electrons to become isoelectronic, meaning they have the same electron configuration with the nearest noble gas. Noble gases have the maximum attraction between nucleus and the minimum repulsion as each other are possible due to the electron configuration. They are stable and do not react, aka inert. Because everybody wants to be like a noble gas. That's the goal. Okay? So, here we go. We're going to do some electron configurations and noble gas stuff here. Ready? First, we're going to do the number of valence electrons here. So this is group 1A, right? 2A. I refer to this as group 3A. Some people could do it 13. Some 15, not 15. 5A, 6A, and 7A, right? The reason why I use the A's tells me the number of valence electrons. So the number of valence electrons here is 1, 2, 3, 5, 6, and 7. Okay? So when I am doing the electron configuration of the valence electrons, this is going to be N, which could be any energy level, S1. That tells me the number of electrons. And S2. Now trust me on this next one here. NS2 NP1, because valence electrons can be S and P only. NS2 NP3 NS2 NP4. This will make a little more sense when I go over electron configurations in the next videos. NS2 NP5. Okay? So when you draw these here, Lewis dot structures, I'm just going to use a generic element here of X for each one. This has one valence electron, so you draw one dot. This has two valence electrons, so you go 1, 2 dots. This has 3 valence electrons, so you go 1, 2, 3 dots. This one right here is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And then the final one has 1, 2, 3, 4, 5, 6, 7. Okay? lose or gain electrons to look like a noble gas here. Okay? The goal is to get to 0 or 8. That's the goal, to look like a noble gas. So the easiest thing for group 1A elements to do, stuff like lithium, is it loses that one electron. Because metals are losers of electrons. Metals are total losers. Okay? Losers. Okay? Group 2, this is the alkali earth metals. These are going to lose 2 electrons. Aluminum, group 3A, it's metal. It's going to lose 3 electrons. Okay? Now we get to the nonmetals. Nonmetals gain electrons here. So we're going to get from 5 to get to 8, we're going to gain 3 electrons. We're going to gain 2 electrons. And we're going to gain 1 electron. Okay? Common charges of these ions. Group 1 likes to form 1 plus. Group 2 likes to form 2 plus. Group 3 likes to form 3 plus. Group 5A goes to 3 minus. Group 6A goes to 2 minus. And group 7A goes to 1 minus. Would the resulting atom be larger or smaller? Well, these are losing electrons, so the resulting ion here would be smaller. Smaller because we're losing electrons. Smaller because we're losing electrons. And then these are going to be larger, larger, and larger because we're gaining electrons. Okay, structure of the ion here. Ready? Okay, so when we do ions here, ions are going to have, oh, you can't even see that, Mr. Harridan. Mr. Harridan. They're going to have brackets when I do ions. Ions have brackets. Okay, so if we started with 1 and we lose 1, our ion is going to have 0 valence electrons. But you still have to put the plus so I know it's an ion. We started with 2, we lost 2. We're going to have 0 electrons. We started with 3, we lost 3. We're going to have 0 electrons. Most metals will have 0 electrons when they do their ion structure. Now we do the nonmetals here. We start with 5 and we gain 3, so now we're going to get to 8 valence electrons. But you still have to do the brackets, and you still have to do the minus 3. We started with 6, we gained 2. You're going to get to 8 valence electrons. Oh, and I wrote that charge backwards. Okay, 2 minus, there we go. There we go. And then finally we start with 7 and gain 1. We get to 8 valence electrons. I think these sunglasses are girl sunglasses. Yeah, anyways. That's what they look like. Okay, you guys are champions. The legend is